People say space is cold, but that sentence is way too simple, and it hides the real danger. But before we continue, please subscribe to the channel to give your support. Let's continue. Your brain learns cold from life on Earth. Cold means winter air, ice, cold water, wind, snow, maybe a freezer. In all of those cases, something is physically touching you or moving around you and carrying heat away. That is how your body understands temperature. You lose heat to air, to water, to metal, to the ground. So you build this very simple idea. Cold is just heat leaving you fast. But space does not work like that, and that is where the problem starts. The first mistake is thinking space is basically like a giant freezer. It is not. A freezer is full of matter. It has air in it, walls around it, and surfaces that can conduct heat. Space is mostly vacuum. That means there is almost no matter there to hold heat and almost no matter there to transfer heat the way you are used to. So when people hear that space is extremely cold, they usually picture the wrong thing. The real issue is not just that space is cold. The real issue is that in space, heat cannot behave in the normal Earth way. On Earth, most of your everyday temperature experience comes from conduction and convection. Conduction is heat moving through direct contact. Convection is heat moving through fluids like air or water. Put your hand on ice, heat leaves your skin through contact. Stand in cold wind, moving air carries heat away from you. Fall into cold water, and heat leaves you even faster because water pulls energy from your body much more efficiently than air does. Now, remove the air, remove the water, remove the pressure, remove almost all surrounding matter. That is space. And at first, that almost sounds safer. If there's no cold air around you, then what is taking your heat away? That sounds like a fair question, but this is exactly where intuition fails. In vacuum, conduction and convection mostly disappear unless you are touching something. That leaves radiation as the main way to gain or lose heat. Radiation is real, powerful, and constant, but it works very differently from cold air or cold water. It depends on your temperature, your surface, what direction you face, whether you are in sunlight, whether you are in shadow, and how much energy you absorb versus how much you emit. So space is not one simple cold environment. It is a place where thermal balance becomes unstable very easily. That leads to the next point, and this is one of the most important numbers in the whole story. The average temperature of the observable universe is set by the cosmic microwave background, about 2.725 Kelvin. That's about minus 270.425 degrees Celsius, or about minus 454.765 degrees Fahrenheit. That is only a tiny amount above absolute zero. That number is not vague, and it is not a guess. It has been measured with very high precision by missions like COBE, WMAP, and Planck. So when we say the background state of the universe is cold, we mean extremely cold in a very exact way. The baseline thermal glow of the universe itself is only about 2.7 degrees above the lowest temperature physics allows anything to approach. That sounds like it should settle the issue. If space is around minus 270 degrees Celsius, then shouldn't anything in space instantly freeze? No, and that is the part that confuses almost everyone the first time they hear it. Astronauts do not instantly freeze in space, and in sunlight, overheating can actually be a bigger immediate problem for a surface than freezing. That sounds contradictory until you separate temperature from heat transfer. A gas can have a temperature, but if there are almost no particles there, it cannot remove your heat efficiently by collision. That is why the vacuum of space does not act like a blast of freezing air. In orbit, the real danger is imbalance. In direct sunlight near Earth, surfaces can heat up to above 120 degrees Celsius or 248 degrees Fahrenheit. In shadow, those same kinds of surfaces can drop below minus 150 degrees Celsius or minus 238 degrees Fahrenheit. So you're not dealing with one number, you're dealing with extremes and almost no natural buffering between them. That buffering is something Earth gives you all the time, and most people never think about it. Our atmosphere spreads heat around. Oceans store heat, winds move it, clouds change it. Pressure stabilizes phase changes. Even when Earth gets very hot or very cold, the planet still smooths out a lot of the chaos. Space does not do that. Space removes the middle layer that makes temperature feel familiar. So the next question is, what does that mean for a spacecraft? It means thermal control becomes a constant engineering fight. Spacecraft cannot rely on air to cool down. They cannot rely on the environment to make temperatures more even. One side may be absorbing strong sunlight while the other side is dumping heat into darkness. Internal electronics are also generating heat the whole time. If that heat is not moved and managed correctly, systems fail. That is why real spacecraft use insulation, reflective surfaces, radiator panels, heat pipes, pumps, fluid loops, and carefully chosen coatings. The International Space Station is a good example. It needs large radiator systems because the station, its electronics, and its crew all produce waste heat. At the same time, it has to protect itself from large temperature swings caused by sunlight and shadow during orbit. Without thermal control, one part of the station could get too hot while the other part becomes dangerously cold. So when people say space is cold, the more correct statement is that space is thermally unforgiving. It does not give you a stable background the way Earth does. It gives you vacuum, radiation, and extreme dependence on position and exposure. And that changes the way you should think about almost everything out there. Planets are shaped by it. Moons are shaped by it. Telescopes are shaped by it. Spacesuits are shaped by it. The design of satellites, landers, probes, and stations all depends on it. Even the way we search for ancient light in the universe depends on controlling heat in conditions where heat no longer behaves in the normal human way. That is the real starting point of this topic. Space is not just cold. It is a place where the usual rules your body trusts stop being enough. Temperature is still real, but the meaning of danger changes. Sometimes the danger is heat building up because it cannot escape fast enough. Sometimes the danger is heat loss into darkness. Sometimes the danger is moving from one extreme to the other with almost no warning and no natural protection. And once you understand that, the whole subject gets more serious very quickly. Because now the question is no longer just how cold space is. The question becomes, how cold can anything possibly get, and why does the universe get so close to that limit without ever fully reaching it? Absolute zero sounds like a simple idea, but it is one of the strangest limits in all of physics. When people hear the phrase, they usually think it just means the coldest cold, the final bottom of temperature, the point where everything freezes completely and all motion stops. That is close enough to start with, but it is still not fully right. Absolute zero is 0 Kelvin, which is minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. And that is not just a very low number on a scale. It is the lowest possible thermal energy a system can have according to physics. That matters because it means there is a real floor under all cold. Temperature is not something that drops forever with no limit. There is a bottom. The universe can get closer and closer to it, but it cannot just keep going downward forever. Now here is where it gets more serious. Absolute zero does not mean matter becomes perfectly dead and motionless in the old classical sense. That picture is too simple. In basic everyday thinking, colder means particles move less, so you might assume that at the very bottom they would stop completely. But quantum mechanics does not allow reality to become that perfectly still. Even at the lowest possible energy state, there is still residual quantum behavior. So absolute zero is not a state of perfect silence. It is the minimum energy allowed by the rules of the universe. That already changes the way you should think about cold. Cold is not just the absence of heat in a casual sense. Cold has a hard limit, and that limit is controlled by deep physics, not by common sense. So the next question is obvious. If absolute zero is the floor, why can nothing ever actually reach it? The answer is one of the clearest and most brutal rules in thermodynamics. Temperature measures the average energy of particles. To make something colder, you remove energy from it. That sounds simple. Remove more energy, get a lower temperature. But the closer you get to absolute zero, the harder every next step becomes. This is the basic meaning of the third law of thermodynamics. You can approach absolute zero, but you cannot reach it in a finite number of steps. In plain language, every stage of cooling becomes more difficult than the one before it. You don't just keep turning down a dial until you hit zero. The closer you get, the more resistant nature becomes. It's like trying to squeeze out the last trace of thermal energy from a system, and the universe keeps refusing to give you the final piece. That is why laboratory physics at ultra-low temperatures is so extreme. Scientists use highly specialized methods like laser cooling, evaporative cooling, magnetic traps, and carefully controlled quantum systems just to get matter unbelievably close to absolute zero. We are talking about microkelvin, which means millionths of a Kelvin above absolute zero, and nanokelvin, which means billionths of a Kelvin above absolute zero. Those are some of the coldest temperatures humanity has ever produced. And this is where the story takes a turn most people don't expect. Space is incredibly cold, but space is not the coldest place we know. That sounds wrong the first time you hear it. Space looks like the ultimate cold environment. Deep space sits near the temperature of the cosmic microwave background, about 2.7 Kelvin. That's far colder than anything in normal human experience. But 2.7 Kelvin is still much warmer than the temperatures achieved in some Earth laboratories. Scientists have cooled atomic gases to less than 1 billionth of a Kelvin above absolute zero. That means tiny controlled experiments on Earth have become colder than most of the universe. That flips the whole idea upside down. Nature made the universe cold on a huge scale, but human beings managed to make something even colder in tiny, highly controlled conditions. So when you say space is cold, that's true, but it's not the final word on cold. The final word takes you into precision quantum experiments, where matter is pushed into conditions more extreme than the background of deep space. And that brings up the next hard question. What is matter even doing at those temperatures? This is where reality gets less intuitive, not more. Even near absolute zero, motion doesn't fully disappear. Particles still have what is called zero-point energy. You don't need the math to understand the point. The point is that the universe cannot be turned into a perfectly still machine. There is always a quantum limit underneath things. And once you get close enough to that limit, matter stops behaving like ordinary matter in the normal, everyday sense. This is the region where superfluids can flow with almost no internal friction. It's where atoms can stop acting like separate individuals and start behaving like one collective quantum state. It's where the ordinary picture of little particles bouncing around gives way to something much stranger. The colder matter gets, the more the hidden rules of quantum mechanics start to dominate what you see. So absolute zero is not only important because it's cold, it's important because it exposes the structure underneath reality. At normal temperatures, heat hides a lot of that complexity. Thermal motion keeps things noisy. At very low temperatures, that noise drops and the deeper rules become easier to see. That's one reason these extreme laboratory experiments matter so much. They are not just trying to break a cold record, they are probing how the universe behaves at its most fundamental level. Now take that idea back out into space, and the stakes get bigger. Cold is not just something that threatens life or damages hardware. Cold also allows fragile structures to exist. When temperatures are low enough, atoms can bind into molecules more easily. Delicate compounds can survive. Gas clouds can lose thermal pressure and become easier for gravity to collapse. That means cold is one of the conditions that helps structure form in the universe. This is especially important in astronomy because a lot of the faintest signals we want to detect are easily drowned out by heat. Infrared astronomy is the clearest example. Warm objects glow in infrared. That means if you build a telescope to detect ancient faint infrared light from distant galaxies, dust clouds, or exoplanet atmospheres, the telescope itself can become a problem. If it's too warm, it produces its own infrared glow and blinds itself. That is why the James Webb Telescope had to be designed to run at cryogenic temperatures. Much of the observatory has to stay below about 50 Kelvin, and one of its instruments, Mercury, has to operate near 7 Kelvin with active cooling. That's incredibly cold, and it's not done for drama. It's done because ancient light is weak, and even a small amount of unwanted heat can bury the signal. So this is the part that changes the meaning of cold again. Cold is not only destructive, cold also makes precision possible. Cold lets chemistry survive. Cold helps stars form. Cold protects faint radiation from being lost in thermal noise. Cold lets us look deeper into cosmic history. That's the real importance of absolute zero in this story. It gives you the lower limit that all cooling is measured against, it shows you that nature has a hard boundary under temperature, and it reveals that the closer you get to that boundary, the stranger and more useful physics becomes. And now the tension gets higher, because if deep space sits near 2.7 Kelvin, where does that number actually come from, and why is the whole universe filled with a faint, ancient glow that has been cooling for billions of years? Space feels empty, but it's not thermally empty, and that changes the whole story. When you look into the night sky, it seems like you're looking into darkness with a few bright objects scattered through it. Stars, planets, maybe a galaxy if the sky is dark enough. But that picture is incomplete. In every direction, across the sky, there is a faint background glow. You can't see it with your eyes, because it's not visible light. It's microwave radiation, and it's everywhere. This is the cosmic microwave background, or CMB. It's one of the biggest reasons space has the temperature it has. And once you understand where it came from, the cold of space stops looking random. It starts looking like history. The key point is this: the universe was not always cold. Early on, it was much hotter and much denser. Matter and light were packed together in a state so energetic that atoms couldn't form in a stable way. Electrons were not bound cleanly to nuclei. Everything was part of a hot plasma. In that state, light couldn't move freely for long distances because it kept interacting with charged particles. The early universe was not transparent. It was more like a hot fog. So what changed? As the universe expanded, it cooled. After about 380,000 years, it had dropped enough in temperature for electrons and nuclei to combine into neutral atoms. Once that happened, light was no longer trapped in the same way. It could finally travel freely through space. That released a flood of radiation into the universe, and that radiation is still here. It's been traveling ever since. But it didn't stay hot. As the universe kept expanding, the wavelength of that radiation stretched. Longer wavelength means lower energy. So over billions of years, what started as much hotter radiation cooled down and shifted into the microwave part of the spectrum. That is why today, when we measure the cosmic background of the universe, we find this extremely cold microwave glow instead of intense visible or higher energy radiation. So when people talk about the cold of space, part of what they are talking about is the faded afterglow of the early universe itself. The cold is not just the absence of stars, it is the leftover thermal signal of a much hotter beginning. Now, here is the number that changed modern cosmology. The average temperature of the cosmic microwave background is about 2.725 Kelvin. That is about minus 270.425 degrees Celsius, or about minus 454.765 degrees Fahrenheit. That is the baseline radiation temperature of the universe today. And this is not one of those broad astronomy estimates where the numbers are rough and people just say about because the real value is uncertain. This has been measured with extraordinary precision. The cosmic microwave background is one of the best measured facts in all of science. That matters because it means we are not guessing about the thermal background of space. We are measuring it directly. The CMB is also extremely uniform, but not perfectly uniform. Its temperature differences from place to place are tiny, only about 1 part in 100,000. That sounds almost insignificant, but those tiny differences are some of the most important patterns in the universe. They are the small early irregularities that later grew under gravity into galaxies, galaxy clusters, and large-scale cosmic structure. So those tiny temperature variations are not noise. They are the early blueprint of the visible universe. This is where the major missions come in. Kobe showed that the cosmic microwave background has an almost perfect black-body spectrum, which means it matches exactly what you would expect from a hot early universe that cooled over time. That was a huge confirmation of modern cosmology. Then WMAP mapped the anisotropies, the tiny directional differences in temperature, in much greater detail. Planck later pushed that even further, giving us an even sharper map of the early universe. So when you say the universe has a background temperature near 2.7 Kelvin, that is not a loose story. That is data, measured, checked, and mapped with extraordinary care. Now the next question is the important one. Why did the whole universe cool down in the first place? The answer is expansion. As space expands, radiation traveling through it gets stretched. Its wavelength gets longer. Longer wavelength means less energy. So expansion cools radiation automatically. You do not need some external refrigerator. The cooling is built into the growth of the universe itself. This is why it is important not to think of the Big Bang as an explosion into cold, empty space. That picture is misleading. The Big Bang was not matter blasting outward into a pre-existing void. It was the early, hot, dense state of space-time itself. Space expanded, and as it expanded, the radiation inside it lost energy by stretching. That is why the universe we live in now is so much colder than the universe that existed near the beginning. So the cold of modern space is not just a condition, it's a record. It's the thermal memory of cosmic expansion. And that brings up another point people often miss. The cosmic microwave background is not only present near stars, planets, or galaxies. It's everywhere. Between galaxies, far from stars, in the darkest regions you can imagine, the CMB is still there. It surrounds everything. It fills all directions. It acts like a baseline radiation bath for the entire observable universe. That means if you took an object and placed it far away from major heat sources, far from stars, far from galaxies, and left it alone for long enough, it would gradually radiate away its own heat and drift toward equilibrium with that background. Not instantly, not dramatically, but over time it would cool toward that 2.7 Kelvin environment. That is a huge idea because it means the universe has a kind of thermal destination. Not absolute zero, at least not now, but a background level that isolated objects tend toward if nothing nearby keeps them warm. This also shows why the word cold in space needs precision. Space is not uniformly one temperature in the practical sense. A spacecraft near the sun can be very hot on one side. A moon can have large day-night extremes. Gas in some regions can be extremely hot even when the density is tiny. But underneath all of that, the cosmic microwave background is still there as the baseline radiation field of the universe. So the cold of space is not just local weather around stars and planets, it has a cosmic floor set by the history of the universe. And now the stakes get bigger again, because once you understand the CMB, you are no longer just talking about why space feels cold to a spacecraft, or why shadow is dangerous to an astronaut. You are talking about the fact that the entire universe has been cooling for about 13.8 billion years. That is the larger truth. The emptiness between stars is not random emptiness. It's part of a long thermodynamic process. The universe began hotter, denser, and more energetic. It expanded, cooled, made atoms, released light, built stars and galaxies, and kept cooling as it aged. Every planet, every galaxy, every living thing exists inside that long downward thermal trend. So, space is cold now, but the deeper point is that the universe became cold through time, and it is still becoming colder. That means cold is not just one property of space, it's part of the story of the universe itself. And once you see that, the next problem becomes even more unsettling. Because if empty space is filled with this ancient background glow, then why does vacuum still make heat behave so differently from anything your body has ever experienced on Earth? Space is dangerous not just because it's cold, but because it's empty, and that is a much bigger problem. When people compare space to cold weather, they are already using the wrong model. Cold weather on Earth still happens within an atmosphere. Even in the middle of a brutal winter, you are surrounded by huge numbers of air molecules. Those molecules hit your skin, your clothes, your face, and they carry heat away. Wind makes that even worse by replacing warmer air near your body with colder air. So when you say a day feels freezing on Earth, what you're really describing is active heat transfer through matter. Space is not like that at all. In space, there may be only a few particles in a cubic centimeter, sometimes much less. In some parts of interstellar space, the average density is so low that it is emptier than many of the best vacuum chambers humans can build in laboratories. And between galaxies, it gets even more extreme. So when people say space is cold, that sentence is missing the most important part. Space is cold, but space is also almost empty. And that emptiness changes the entire way heat works. That is why cold air is the wrong comparison. Air is matter. Air can transfer energy quickly. Vacuum cannot do that in the same way. So the danger in space is not that you are standing inside super cold wind. The danger is that the normal thermal systems your body depends on are gone. And once you understand that, the next part becomes much clearer and much worse. Your intuition about heat transfer starts failing almost immediately. There are three main ways heat moves. Conduction is heat transfer through direct contact. Convection is heat transfer through moving fluids like air or water. Radiation is heat transfer through electromagnetic energy, which does not need matter in between. On Earth, conduction and convection dominate a lot of daily life. Sit on a cold metal bench and you feel conduction. Stand in cold wind and you feel convection. Fall into icy water and both the contact and the movement of water strip heat from your body very fast. In vacuum, most of that disappears. If you are not touching something, conduction is mostly gone. If there is no air or fluid moving around you, convection is gone too. That leaves radiation as the main process, and radiation does not care about your instincts. It does not feel like wind, it does not feel like icy air, and it does not produce the kind of immediate feedback your body is used to. But it still controls whether something gains heat or loses heat. This is why a spacecraft can have one surface in sunlight getting extremely hot, while another surface in shadow becomes cryogenic. There is no atmosphere around it to smooth the temperatures out. There is no wind, no air circulation, no natural moderation. One side absorbs energy from the sun, the other side dumps energy into darkness, and the difference can become extreme very quickly. That is also why thermal design in space is so difficult. On Earth, engineers can often count on air to remove some heat, or at least spread it around. In space, that option is mostly gone. Heat has to be moved deliberately through the spacecraft and then radiated away on purpose. If you get that wrong, systems overheat, freeze, or cycle between both. Now take that idea one step further and things start getting strange in a way most people never think about. In vacuum, boiling and freezing can happen together. That sounds impossible at first, but it makes sense once you remember that pressure matters. Water does not only care about temperature, it also cares about surrounding pressure. In very low pressure conditions, water can boil at much lower temperatures than it does at sea level. So if liquid water is suddenly exposed to a vacuum-like environment, part of it can start boiling off very quickly. But as that happens, the evaporation pulls energy out of the remaining liquid. That cooling can be so strong that what is left starts freezing. So you can have the same substance moving toward vapor loss and freezing at the same time. That is not science fiction, and it's not some weird edge case invented for drama. It's basic phase behavior under low pressure. Vacuum changes the rules for liquids in a way that most people never have to deal with on Earth. That matters because it shows that vacuum is not just very cold. Vacuum changes how materials behave. It changes boiling points, freezing behavior, heat flow, and pressure balance. So when you put matter into space, you are not just exposing it to low temperature, you are exposing it to a different physical regime. And that leads directly to the human question, because if vacuum changes heat transfer this much, what does it mean for your body? It means your body cannot manage itself out there, not even close. A spacesuit is not just protection from impact or a way to hold oxygen. It's a portable life support system and a portable thermal control system at the same time. In normal language, it's a wearable climate machine. Without it, the human body is operating in conditions it was never built to survive. Your body constantly produces heat. Even at rest, a human gives off around 100 watts of power. When working hard, that can rise much higher. On Earth, your body gets rid of that heat using blood flow, sweating, breathing, and heat exchange with the surrounding air. But in vacuum, those normal methods stop working the way they're supposed to. Sweat does not cool you in the normal way because the pressure environment is wrong. Air is not there to carry heat away. The external conditions can swing from intense sunlight to deep shadow with almost no buffer. So the suit has to manage all of that for you. That is why EVA suits use pressure systems, insulation, reflective layers, and liquid cooling garments. The liquid cooling system is especially important because astronauts can generate a lot of waste heat while working. Water circulating through tubes inside the suit helps remove that heat from the body. At the same time, the outer layers help prevent dangerous heat gain from sunlight and dangerous heat loss in shadow. So the suit is fighting in both directions at once. It's not just trying to stop you from freezing, it's trying to stop you from overheating. That is one of the most important points in this whole topic. In space, thermal danger is not one-directional. It's not just about getting too cold. It's about losing the stable middle ground that Earth gives you for free. That is really the main lesson here. The danger in space is not one dramatic number on a thermometer. The danger is lack of moderation. On Earth, the atmosphere moderates temperatures. Oceans store heat and release it slowly. Winds move energy around. Pressure keeps materials behaving in familiar ways. Weather can be harsh, but the planet still gives you a huge thermal buffer. Space removes that buffer. It removes the air, removes the pressure, removes the smoothing effect, and leaves you with radiation, exposure, and direct physical limits. That is why the word cold is not enough. It sounds simple, but the real threat is more severe than that. Space is a place where heat can no longer be trusted to behave in a familiar way. And once those protections are gone, small changes in position, sunlight, surface type, or shielding can decide whether something survives. And now the tension rises again because once you understand that vacuum is the real problem, not just low temperature, the next question becomes even more brutal. How can one side of a spacecraft be hot enough to burn while the universe around it still sits only a few degrees above absolute zero? Space can be only a few degrees above absolute zero in the background and still burn a spacecraft at the same time. That sounds wrong, but it is one of the most important facts about space. People hear that the universe is extremely cold and they assume that anything out there should just freeze. But near Earth and in many other parts of space, sunlight is strong enough to create the opposite problem. So the real danger is not one steady temperature. The real danger is the split between direct sunlight and deep shadow. Near Earth orbit, direct sunlight delivers about 1,361 watts of energy per square meter. That is called the solar constant at Earth's distance from the sun. In normal language, it means sunlight in space hits hard. On Earth, the atmosphere absorbs and scatters part of that incoming energy. In space, there is no protective layer above you doing that job. So if a surface is facing the sun, it can heat up fast. Then move that same surface into shadow and the situation changes completely. Now it is no longer absorbing solar energy, but it is still radiating its own heat away. In vacuum, with no air around to moderate the temperature, cooling can become extreme. So one side can be getting cooked by sunlight, while another side is losing heat into darkness. That is normal in orbit. That is not some rare edge case. That is the default thermal reality of spaceflight. This is why the phrase, "space is cold," is incomplete to the point of being misleading. Space is not one giant freezer. Space gives you sharp thermal extremes with very little in the middle. That becomes obvious when you look at real spacecraft surfaces. External temperatures can range from around positive 120 degrees Celsius or about 248 degrees Fahrenheit, down to around minus 150 degrees Celsius, or about minus 238 degrees Fahrenheit. In some cases, the range can be even wider depending on the shape of the spacecraft, the surface materials, how fast it rotates, what parts face the sun, and how its coatings handle radiation. Those numbers are not just interesting engineering facts. They decide whether a mission works or fails. At those temperatures, materials expand and contract differently. Lubricants can stop behaving the way they should. Seals can fail. Electronics can drift out of their safe operating range. Batteries can lose performance. Sensors can become inaccurate. Even small design mistakes can turn into mission-ending problems if thermal control is not handled correctly. So spacecraft do not just need engines, fuel, and computers. They need constant thermal management. A spacecraft is not just trying to move through space, it is trying to stay inside a survivable temperature range while the environment keeps trying to push different parts of it toward opposite extremes. And if you want a simple example of how severe that can get, look at the moon. The moon is close to Earth, close to the sun on a cosmic scale, and still one of the clearest demonstrations of how violent space temperatures can be. Near the lunar equator, daytime surface temperatures can climb to around 127 degrees Celsius, or about 261 degrees Fahrenheit. Then, during the long lunar night, those temperatures can fall to about minus 173 degrees Celsius, or about minus 279 degrees Fahrenheit. Same world, same surface, completely different temperature, depending almost entirely on whether sunlight is hitting it. And the moon is a perfect example because it has almost no atmosphere to spread heat around. On Earth, air and weather soften the difference between day and night. On the moon, there is no thick atmospheric blanket to absorb, circulate, and slowly release energy. If the sun is up, the surface can get brutally hot. If the sun is down, the heat escapes and the surface becomes brutally cold. That means lunar exploration is not just a problem of distance, landing, and dust. It is also a problem of surviving one of the harshest thermal cycles in the inner solar system. A lunar rover, habitat, or spacesuit cannot just be designed for cold space. It has to handle both intense heating and intense cooling, often within the same mission profile. Now, this raises another question that sounds almost too simple, but in space it becomes critical. What kind of surface handles this best? The answer is, the finish of a spacecraft matters far more than most people would expect. In space, color, texture, and coating are not cosmetic details. They are survival tools. A white or highly reflective surface can reduce how much solar energy gets absorbed. That helps keep some parts of a spacecraft cooler when facing the sun. Radiator panels are often designed to do the opposite in another direction. They are made to emit waste heat efficiently so the spacecraft can dump excess thermal energy into space. Multi-layer insulation helps reduce unwanted heat gain and heat loss. The angle of a panel matters. The orientation of the spacecraft matters. The optical properties of a surface matter. So in space, black and white are not just colors, they are thermal decisions. That is one reason spacecraft often look the way they do. Their surfaces are shaped not just by structure or aesthetics, but by heat control. Reflective foils, insulated blankets, radiator panels, and specialized coatings are all part of keeping the vehicle alive. On Earth, a badly chosen surface color might make your car hotter in the sun. In space, a badly chosen surface finish can damage equipment, shorten mission life, or destroy sensitive instruments. And once you understand that, the movie version of cold space falls apart completely. The usual simplified image is that space is one endless frozen void, and anything out there just gets colder and colder. But the real situation is more harsh and more technical than that. In space, heat and cold are not broad moods set by the environment. They are the result of geometry, radiation, and exposure. Are you facing the sun or not? Are you insulated or not? Are you designed to absorb heat or reject it? Are you rotating? Are you in orbit? Are you above a bright planet that reflects light back at you? Are you near a star or far from one? That is what decides whether something gets hotter or colder. So the real truth is not that space is one giant freezer. The real truth is that space gives you almost no middle ground. It can expose one surface to intense solar heating while another surface falls toward cryogenic cold. It can force engineers to think about every angle, every coating, every layer of insulation, and every watt of waste heat inside a machine. And that should change how you think about every world in the solar system too. Because once sunlight and vacuum start working together like this, the next question is inevitable. If one place near the sun can be hot enough to melt lead by day and deadly cold by night, then how different can cold really be from one world to another? Cold in space is not one number, and if you think it is, the solar system breaks that idea immediately. A lot of people reduce it to one simple rule. Close to the sun means hot, far from the sun means cold. That sounds reasonable, and at a very basic level it is partly true, but it is nowhere near enough. If that rule were the full story, planets and moons would be much easier to understand. They are not. The real thermal story depends on atmosphere, rotation, surface properties, pressure, reflectivity, internal heat, and how long a world stays in sunlight or darkness. Distance matters, but distance alone does not explain what cold really looks like in space. Mercury is the cleanest place to start because it looks like it should be simple and then immediately proves it is not. Mercury is the closest planet to the sun, so yes, its day side gets extremely hot. Daytime temperatures can reach around 430 degrees Celsius, or about 806 degrees Fahrenheit. But Mercury does not have a substantial atmosphere to hold heat and spread it around well, so once the sun is gone, the temperature crashes. Nighttime temperatures can fall to roughly minus 180 degrees Celsius, or about minus 292 degrees Fahrenheit. Same planet, same surface, completely different thermal reality depending on whether sunlight is present. That is one of the clearest proofs that being close to the sun does not protect the world from extreme cold. And Mercury is not just a weird exception. The moon repeats the same lesson much closer to home. The moon has a very long day-night cycle, with roughly 2 weeks of daylight followed by roughly 2 weeks of night at a given location. It has no dense atmosphere, no oceans, and almost none of the thermal smoothing Earth gives you for free. That is why the lunar surface can rise to around 127 degrees Celsius, or about 261 degrees Fahrenheit in sunlight, then drop to around minus 173 degrees Celsius, or about minus 279 degrees Fahrenheit, during the long lunar night. So even in Earth's neighborhood, cold space is not one steady condition. It's exposure, isolation, and time acting together. Now push far outward and the picture changes again. Pluto is much farther from the sun, averaging roughly 39 astronomical units away, and its surface temperatures are around 40 to 60 Kelvin. That is about minus 233 to minus 213 degrees Celsius, or about minus 387 to minus 351 degrees Fahrenheit. Those numbers are far outside normal human experience. But Pluto is not a dead frozen rock. New Horizons showed a world with volatile ices, a thin atmosphere, and signs of active geology. Its atmosphere can expand and contract with the seasons, which means even at these cryogenic temperatures, Pluto is still changing. So extreme cold does not automatically mean complete stillness. That is where the story gets even stranger, because once you accept that Pluto can still be active at those temperatures, Triton stops looking impossible and starts looking like the next warning. Triton, Neptune's largest moon, has surface temperatures near 38 Kelvin, around minus 235 degrees Celsius, or about minus 391 degrees Fahrenheit. That makes it one of the coldest directly measured bodies in the solar system. And yet, Voyager 2 saw evidence of geyser-like plumes there. In other words, one of the coldest known surfaces in the solar system still showed active processes. That should destroy any simple idea that cold means inert. Sometimes these worlds stay active because energy is trapped, redirected, or released in unfamiliar ways. Extreme cold does not end physics. It changes which physics dominates. So what is the real lesson from all of this? It is that cold is local, contextual, and deceptive. You can't just line worlds up by distance from the sun and say the story is finished. Mercury is close to the sun and still gets brutally cold at night because it cannot hold heat well. The moon shows huge thermal swings because it lacks atmosphere and has long periods of daylight and darkness. Pluto is cryogenic but still dynamic. Triton is even colder and still shows activity. Once you look closely, simple ranking systems stop working. Reflectivity matters, pressure matters, rotation matters, internal heat matters, tidal flexing matters, surface composition matters. Thermal reality in space is built from multiple factors at once. And that's the deeper point. Space doesn't just break human comfort, it breaks simple rules. The phrase cold space sounds clean and easy, but real worlds don't obey that kind of shortcut. Some places are hot by day and deadly cold at night. Some places stay deep frozen yet remain geologically active. Some places look dead from a distance and turn out to be thermally complex when you actually measure them. So the more you zoom out, the less cold behaves like a single thing. It starts behaving like a whole category of environments, each shaped by its own combination of sunlight, vacuum, chemistry, timing, and hidden energy sources. And once that idea is in place, the next step gets even intense, because once you accept that Pluto can still be active at those temperatures, Triton stops looking impossible and starts looking like the next warning. Triton, Neptune's largest moon, has surface temperatures near 38 Kelvin, around minus 235 degrees Celsius, or about minus 391 degrees Fahrenheit. That makes it one of the coldest directly measured bodies in the solar system. And yet, Voyager 2 saw evidence of geyser-like plumes there. In other words, one of the coldest known surfaces in the solar system still showed active processes. That should destroy any simple idea that cold means inert. Sometimes these worlds stay active because energy is trapped, redirected, or released in unfamiliar ways. Extreme cold does not end physics. It changes which physics dominates. So what is the real lesson from all of this? It is that cold is local, contextual, and deceptive. You can't just line worlds up by distance from the sun and say the story is finished. Mercury is close to the sun and still gets brutally cold at night because it cannot hold heat well. The moon shows huge thermal swings because it lacks atmosphere and has long periods of daylight and darkness. Pluto is cryogenic but still dynamic. Triton is even colder and still shows activity. Once you look closely, simple ranking systems stop working. Reflectivity matters, pressure matters, rotation matters, internal heat matters, tidal flexing matters, surface composition matters. Thermal reality in space is built from multiple factors at once. And that's the deeper point. Space doesn't just break human comfort, it breaks simple rules. The phrase cold space sounds clean and easy, but real worlds don't obey that kind of shortcut. Some places are hot by day and deadly cold at night. Some places stay deep frozen yet remain geologically active. Some places look dead from a distance and turn out to be thermally complex when you actually measure them. So the more you zoom out, the less cold behaves like a single thing. It starts behaving like a whole category of environments, each shaped by its own combination of sunlight, vacuum, chemistry, timing, and hidden energy sources. And once that idea is in place, the next step gets even intense, because once you accept that Pluto can still be active at those temperatures, Triton stops looking impossible and starts looking like the next warning. The universe has a background temperature, but even that is not always the coldest thing out there. That sounds like it should be impossible. If deep space is filled with the cosmic microwave background at about 2.7 Kelvin, then it feels like that should be the lowest natural baseline anything can have. And most of the time, for isolated objects, that's roughly true. Left alone long enough, things tend to cool towards that background. But nature doesn't always stay near the average. Under the right conditions, it can create places that drop even lower. The Boomerang Nebula is one of the best examples of that, and it's one of the strangest cold objects ever observed. Its gas has been measured at around 1 Kelvin. That's about minus 272.15 degrees Celsius, or about minus 457.87 degrees Fahrenheit. That makes it one of the coldest directly measured bodies in the solar system. So now the question becomes very direct. How can anything in the universe be colder than the universe's own background radiation? The answer is rapid expansion. When gas expands very quickly, it cools. This is a real physical process called adiabatic cooling. You don't need the equations to understand the idea. The basic point is that if gas is forced to expand fast enough, its internal energy drops and its temperature falls. The Boomerang Nebula appears to be a case where that process happens on a huge scale. It's thought to be the result of a dying star throwing off material at extremely high speed. The outflow is on the order of hundreds of kilometers per second. That means the gas is being driven outward violently, expanding as it goes, and cooling so much in the process that it drops below the 2.7 Kelvin background of the universe itself. That's what makes this object so important. It's not just cold in the usual space sense, it's colder than the afterglow of the Big Bang that fills the rest of the sky. And that should immediately change how you think about space temperature. There is no single temperature of space that tells the whole story. There is a cosmic background, yes, but then there are also local conditions, local energy flows, and extreme events that can push matter above or below that background. The universe is not thermally flat. It has structure, gradients, exceptions, and rare environments that break the simple version of the rule. That is exactly what the Boomerang Nebula proves. And this is not some loose theoretical claim. It is based on observation. Astronomers studied the nebula using radio and millimeter wave measurements, especially from molecules like carbon monoxide. Those molecules emit and absorb radiation at specific frequencies. By looking at those spectral lines, scientists can work out how the gas is moving, how dense it is, and how cold it has become. That is a big point, because from far away, a nebula can just look like a strange cloud in space. But once you measure the light carefully, it stops being just a cloud and starts becoming a thermodynamic system you can read in detail. The shape, the motion, the line strengths, the emission patterns, all of that turns into evidence. So the Boomerang Nebula is not cold because someone guessed it was cold. It is cold because the data show gas expanding so fast and behaving in such a specific way that the temperature can be inferred from real measurements. That matters for another reason too. It proves that the background temperature of the universe is not always the local minimum. It is the average radiation bath, but under unusual conditions, matter can temporarily cool below it. That means even the coldest large-scale background in the universe is not the full lower limit for local environments. And that raises the tension again, because once you accept that, the picture gets more serious. Space is not just cold on average. Space contains regions so extreme that they can outdo the background of the universe itself. It can create natural pockets that are colder than the ancient microwave glow left over from the early cosmos. That is why the Boomerang Nebula is such a powerful example in the story. It destroys the idea that cold in space is simple, smooth, and uniform. It shows that cosmic cold has dynamics. It has mechanisms. It has rare cases where matter gets pushed into thermal states that seem impossible until you understand the physics behind them. And this changes the emotional scale of the subject too. Earlier, the story was that space is only a few degrees above absolute zero. That was already extreme. Now the story becomes even sharper. Even that background is not always the bottom locally. Given the right outflow, the right expansion, and the right environment, nature can go lower. So space is colder than most people think, and in rare cases, it is colder than the universe's own leftover heat. And once that's true, the next question becomes even more important. Because if extreme cold can do this to gas in a nebula, then what role does cold play in building much larger structures, like the clouds that collapse into stars? Some of the coldest places in space are not where things die. They are where stars begin. That is one of the biggest reversals in this whole topic. Up to this point, cold has sounded like a threat, and for humans it absolutely is. Cold in space can destroy machines, break your intuition, and make survival impossible without technology. But when you zoom out and look at how the universe actually builds things, cold starts doing the opposite. In many cases, cold is not the enemy of creation. Cold is one of the conditions that makes creation possible. The best place to see that is inside molecular clouds and dark nebulae. These are huge clouds of gas and dust drifting through space, and many of them are extremely cold. Typical temperatures can sit around 10 to 20 Kelvin. That's about minus 263 to minus 253 degrees Celsius, or about minus 441 to minus 423 degrees Fahrenheit. Those numbers are so far below human experience that they almost stop feeling real. But these clouds are not dead zones. They are some of the most important structures in the galaxy. They are stellar nurseries. That sounds strange at first because people usually connect stars with heat, brightness, and violent energy. And that's true once the star is fully formed. But before a star shines, before fusion starts, before the object becomes bright and stable, it begins in darkness and cold. It begins in a region where gas is dense enough and cold enough for gravity to start taking over. That is why temperature matters so much here. Hot gas pushes back. Its particles move faster, and that internal motion creates pressure that resists collapse. If a cloud is too warm, gravity has a harder time pulling it inward. But when gas is cold, the particles move slower. The cloud has less thermal pressure pushing outward. That gives gravity a better chance to win. And that is not a side detail. That is one of the core reasons stars can form at all. A cold cloud can start to fragment. Different regions can become dense enough to collapse under their own gravity. Those collapsing knots become protostars, the early stage of star formation. Over time, material keeps falling inward. Pressure rises, temperature rises in the center, and eventually, if enough mass builds up, nuclear fusion begins. A star is born. So, in a very direct sense, the cold of space helps make stars possible. Without low temperatures in these clouds, the gas would resist collapse much more strongly, and star formation would be much harder. That alone already changes the meaning of cold, but it gets even more interesting when you look at the chemistry inside these clouds. Cold interstellar regions are not chemically empty. In fact, they are chemically rich in a way that surprises a lot of people. Astronomers have detected water, carbon monoxide, ammonia, methanol, and the long list of other molecules in interstellar space, including many organic molecules. Some form in the gas itself, and some form on the surfaces of tiny dust grains. That happens because dust grains in these clouds act like little chemical workbenches. Atoms and molecules can stick to them, interact, and sometimes combine into more complex compounds. In warmer environments, many fragile molecules would be broken apart more easily by heat or harsh radiation. In colder, shielded regions, they can survive long enough to build up. So yes, cold can slow some reactions down, but it also protects structures that would not last in hotter places. It gives the universe a way to preserve delicate chemistry. That is a very important shift in the story. Cold is not only removing energy. Cold is creating conditions where certain kinds of matter can exist, combine, and persist. And there's another reason this matters. These clouds are usually dark and visible light. If you point a normal optical telescope at a dense molecular cloud, a lot of the inside is hidden. Dust blocks visible wavelengths very effectively, so to really study what's going on, astronomers have to look in other parts of the spectrum. This is where radio, millimeter wave, and infrared astronomy become essential. Instruments like ALMA, Herschel, and JWST can detect the signatures that visible light misses. They can measure the temperatures, densities, and chemical fingerprints inside these cold clouds. They can show where molecules are concentrated, where gas is collapsing, and where young stars are beginning to form behind the dust. That is why these clouds are such a big deal scientifically. They may look dark, but they are not empty. The darkness is full of information. It is full of structure, motion, and chemistry. It is full of hidden activity. And that is the part that makes this section so important for the overall script. Up to now, cold has mostly sounded hostile. It can kill you, damage spacecraft, freeze worlds, and push matter into extreme states. All of that is true. But here the story turns. Cold is also productive. Cold is one of the reasons the universe can organize itself into something more complex. Cold lets gas clouds lose enough pressure for gravity to pull them inward. Cold protects molecules. Cold helps dark clouds become star-forming regions. And once stars form, planets can eventually form around them. So the same deep space cold that would destroy an unprotected human body is also part of the chain of events that made planets, chemistry, and life possible in the first place. That is a big reversal, and it raises the stakes again, because now cold is no longer just something to survive. It is part of the machinery of the cosmos. It is part of how the universe builds itself. And once you understand that, the next question becomes harder to ignore. If cold shapes the birth of stars, then what happens to the machines we send into space, especially when they have to survive far from the sun, where warmth becomes scarce and the deep freeze starts winning? The farther a spacecraft goes from the sun, the more cold stops being a background condition and starts becoming a direct engineering threat. A lot of people think the main challenge of space missions is getting off Earth or navigating through space or landing somewhere difficult. Those are all real problems, but there is another problem running through almost every mission, and it never goes away. Spacecraft have to survive thermally. They have to stay within operating temperature limits while moving through an environment that does not care what their systems need. Voyager is one of the clearest examples of that. The Voyager probes went through the outer solar system and then kept going. As they moved farther from the sun, sunlight became dramatically weaker. By the time you get out to Neptune's distance, sunlight is only about 1/900th as intense as it is at Earth. That means a spacecraft out there gets almost none of the passive solar warmth that missions near Earth can still rely on. And that changes the whole thermal picture. Closer to the sun, a spacecraft may spend a lot of effort avoiding overheating. Farther out, staying warm enough becomes a major part of survival. Every system has a safe temperature range. If the spacecraft drops below it, things stop working the way they should. So a mission like Voyager is not just cruising through darkness. It is constantly fighting to keep critical parts of itself from getting too cold. That matters because electronics do not like cryogenic conditions unless they were specifically designed for them. Batteries lose performance. Propellant lines can have problems. Lubricants can thicken or stop behaving properly. Materials can become brittle. Circuits can drift outside their intended behavior. Sensors can fail or give unreliable readings. Even small temperature changes can have major effects if a system is already near its limit. So when people picture a spacecraft as a sealed metal machine, they often miss the fact that it's really a thermal-sensitive system from front to back. That is why deep space missions use insulation, heaters, thermal coatings, and in some cases, radioisotope power systems that provide both electricity and useful heat. Thermal louvers and other control methods help manage how much heat is retained or rejected. A spacecraft is always dealing with internal heat from electronics and power systems, but it is also always losing heat to space. The job is to control that balance carefully enough that the mission survives. So even in deep space, where the public tends to picture silent, empty darkness, engineering is still a constant fight over heat flow. In many missions, freezing is not just a side risk, it's one of the core design problems. Now here is where the story flips again, because sometimes the goal is not to avoid getting cold, sometimes the goal is to become extremely cold on purpose. The James Webb Space Telescope is one of the best examples of that. JWST was built mainly to observe the universe in infrared, and that creates a problem that sounds simple but turns out to be fundamental. Warm objects emit infrared. That means if your telescope is warm, the telescope itself glows in infrared. And if you are trying to detect faint ancient infrared light from very distant galaxies, dust clouds, or exoplanet atmospheres, your own telescope can drown out the signal. So to see the cold and faint universe, the observatory itself has to become cold. That is why JWST has its giant sun shield. It blocks light and heat from the sun, Earth, and Moon, so the telescope side can cool down dramatically. Large parts of the observatory operate below about 50 Kelvin. That's around negative 223 degrees Celsius or about negative 370 degrees Fahrenheit. And one of its most important instruments, Mercury, has to go even colder to around 7 Kelvin, which is about negative 266 degrees Celsius or about negative 447 degrees Fahrenheit, using active cryocooling. That means one of humanity's most advanced telescopes had to be turned into one of the coldest major observatories ever deployed, just so it could do its job. And this gets to a very important point. Cold in space is not only a problem engineers fight against, sometimes it's the thing that makes the science possible. Infrared astronomy depends on this. If you want to study ancient galaxies whose light has been stretched by cosmic expansion, or dusty star-forming regions hidden behind visible light-blocking material, or exoplanet atmospheres, you need to detect very faint infrared signals. If your observatory is too warm, it contaminates the measurement. So by going cold, you reduce your own thermal noise and gain access to parts of the universe that would otherwise stay hidden. That is why the thermal harshness of space can become an advantage. The same basic physics that threatens spacecraft can also be used to make them better scientific tools. And once you see that, the whole topic becomes broader. Thermal control is not just about survival, it's about mission capability. A spacecraft has to be warm enough where systems need warmth, cold enough where instruments need noise, and stable enough that all of this works for years in an environment with no natural moderation.
That is true for deep space probes, but it is also true much closer to home. A Mars rover has to survive cold nights that can shut systems down if heat is not managed carefully. A lunar lander has to deal with long periods of sunlight and long periods of freezing darkness. A satellite in orbit around Earth still has to manage repeated transitions between sunlight and shadow. Every mission has its own thermal problem, but none of them get to ignore it. That is the real pattern here. Heat flow is always part of the mission architecture. It shapes hardware choices, power systems, insulation, instrument design, operations, and even where a spacecraft can point itself safely. Space never lets you forget that temperature is a systems-level problem. And that increases the tension again, because once you understand that even our machines struggle with cold, the next question gets stranger. If empty space, planets, moons, and spacecraft are all shaped by thermal limits, then what happens when you get to something even more extreme? Something people assume should just be a frozen dark object, but turns out to have a temperature story that is far stranger than that. Black holes sound like they should be the ultimate cold, dead objects, but that is not actually the right way to think about them. The name pushes your brain in the wrong direction. Black hole sounds like pure darkness, no light, no energy, no escape, just a dead frozen pit in space. And visually, that is part of why black holes are so powerful in people's imaginations. They look like the end of everything. But once physics enters the story, the picture gets much stranger. Black holes are not just dark objects sitting outside thermodynamics. They have temperature, and the way that temperature works is one of the most counterintuitive ideas in modern science. This comes from Hawking radiation. The basic idea is that black holes are not perfectly black in the thermodynamic sense. Because of quantum effects near the event horizon, black holes can be associated with a temperature and can radiate energy. That means a black hole is not completely cut off from the rest of physics. It has entropy, it has temperature, and over extremely long timescales, it can lose energy. Now, here's the part that sounds backwards the first time you hear it. A black hole's temperature goes down as its mass goes up. So for black holes, bigger means colder. That is the opposite of how most people expect this to work. A larger black hole feels like it should be more intense in every way. And in some ways it is, but its Hawking temperature is actually lower than that of a smaller black hole. A stellar mass black hole, the kind formed from the collapse of a massive star, has a Hawking temperature that is absurdly tiny. It is far below the temperature of the cosmic microwave background. That has an important consequence. Right now, in the current universe, a typical stellar mass black hole is colder than the background radiation around it. That means it absorbs more energy from the universe than it emits through Hawking radiation. So even though black holes technically radiate, the effect is completely overwhelmed by the fact that the universe around them is warmer. That already breaks the simple idea of black holes as just frozen darkness. They are colder than the universe's background, but not in the ordinary way that a block of ice is colder than room air. Their temperature is tied to quantum effects and gravity in a way that does not match everyday experience at all. And then it gets even stranger. Supermassive black holes, the ones sitting in the centers of galaxies, are even colder. Since larger mass means lower Hawking temperature, a supermassive black hole has a temperature even closer to zero than a stellar mass black hole does. In practical terms, its Hawking temperature is so tiny that it's almost impossible to treat it as a normal source of radiation in the present-day universe. It's completely buried under the much warmer background around it. So if you're trying to think of black holes as objects with a temperature, the first thing to understand is this. The larger the black hole, the less its Hawking temperature looks like anything intuitive. These are not cold objects in the normal sense. They are systems where gravity, quantum effects, and thermodynamics combine to produce a temperature that is real, but deeply non-human in meaning. Now comes the next reversal, because while the black hole itself can have an incredibly tiny Hawking temperature, the region around it can be one of the hottest places in the universe. That's where accretion enters the picture. When gas and dust fall toward a black hole, they usually don't just drop straight and cleanly. They form an accretion disk, a rotating structure of matter spiraling inward. As that material collides, compresses, and experiences huge friction-like heating effects, it can become extremely hot, sometimes reaching millions of degrees. In some cases, the gas emits strong X-rays and other high-energy radiation. So now look at what that means. In the same overall system, the black hole itself can be associated with an extremely tiny Hawking temperature, while the matter around it is glowing at temperatures hot enough to produce some of the most energetic radiation we observe. Same system, opposite extremes. And that's exactly why black holes matter in this script. They push beyond the simple idea that cold in space is just about low temperatures in empty regions. Black holes show that cold can become part of a much deeper and stranger framework. Here, temperature is no longer just about environment. It's tied to the most fundamental structure of physics. Because once you start talking about black hole temperature, you also have to talk about black hole entropy. And once you talk about entropy, you're right in the middle of one of the deepest problems in theoretical physics. Black holes connect gravity, quantum mechanics, and thermodynamics. Those are three of the biggest frameworks we have for describing reality. And black holes sit right where all three start interacting in uncomfortable ways. That's why this topic matters so much. It means cold is not just something out in the environment, like the temperature of deep space or the surface of a moon. Cold can also be a clue to hidden laws of the universe. It can tell you something about information, energy, space-time, and the limits of our current theories. So when you say black holes aren't cold in the way people think, what you really mean is that you force you to update the whole meaning of temperature. A black hole can be colder than the cosmic microwave background, but its surroundings can be violently hot. Its temperature can be lower when its mass is bigger, and the reason it has a temperature at all leads straight into some of the hardest questions in science. That is why this section raises the stakes. Up to now, cold has already done a lot. It has broken your intuition, shaped planets and moons, controlled spacecraft design, and helped build stars. But here, it goes further. Here, cold becomes part of the hidden architecture of modern physics. And once the story reaches that level, the next question becomes much more personal. Because after talking about planets, telescopes, nebulae, and black holes, the viewer naturally asks the simplest and most frightening version of all of this. What would actually happen to your body if all the protection of Earth disappeared and you were exposed to space directly? The movie version is wrong, and the real version is worse. A lot of people think that if you were exposed to space without a suit, you would instantly freeze solid, like your body would turn to ice in one dramatic second. That is not what would happen. Space is deadly, but not in that clean, simple, cinematic way.
The first things that would kill you are loss of pressure and loss of oxygen, not instant freezing. In vacuum, your body is suddenly outside the pressure range it was built for. Air in your lungs becomes a problem immediately. Oxygen stops reaching your brain. You would lose useful consciousness very fast, in seconds, because your brain cannot function without oxygen delivery. At the same time, body tissues would begin to swell because of the pressure drop. Not explode, not like in a movie, but swell. Fluids near the surface can start behaving abnormally under vacuum conditions. This is already catastrophic long before freezing becomes the main issue. That matters because it changes the whole image. The real danger is not one dramatic effect. It is a sequence of failures happening at once, and your body loses that fight very quickly. Now that raises the next question. If space is so cold, why would freezing not be immediate? Because vacuum does not remove heat the way cold air or cold water does. In space, your body would still radiate heat away, but radiation is slower than the heat loss you can get through dense matter. Cold water on Earth can strip heat away from your body much faster than vacuum can, because water is in direct contact with you and conducts heat away very efficiently. Cold air can also cool you faster than empty space in some situations, especially if wind is involved. So yes, space is thermally extreme, but no, it does not freeze you instantly. That is one of the most important intuition breaks in this whole topic. The background temperature of space is lower, but the speed of heat extraction depends on how heat is being transferred. Vacuum changes that completely. That does not make thermal danger small, it just means it is not the first thing that kills you. Without a suit, your body would keep losing heat by radiation. If you were in direct sunlight, overheating could also become a problem depending on exposure and orientation. If you were in shadow, heat loss would continue without any natural atmospheric buffer. So thermal stress is real, but it comes as part of a larger collapse. Space does not kill you with one clean mechanism. It kills through pressure failure, oxygen failure, fluid and gas behavior changing, and then continued thermal imbalance on top of all that. That is why the truth is more disturbing than the movie version. The movie gives you one simple image. Physics gives you multiple simultaneous failures. And this is where the comparison to cold water becomes useful, because it breaks another very common misconception. If you fell into icy water on Earth, hypothermia could become a major danger very quickly, often faster than vacuum would cool your body. That sounds backwards at first, but it's true in the basic physical sense. Water is dense. Water touches your body directly. Water conducts heat away much better than air does and vastly better than empty space does. So even though space has a much lower background temperature than an icy lake, the icy lake can pull heat out of you faster than vacuum can. That comparison matters because it makes the point in a very simple way. Space is colder as an environment, but not necessarily faster at draining your body heat than dense matter is. Again, temperature and heat transfer are not the same thing. So now the next question becomes obvious. How do astronauts survive at all? The answer is that a spacesuit is not just protective clothing, it's a life support system wrapped around a person. It manages pressure, breathing gas, carbon dioxide removal, and thermal control all at once. In practical terms, it functions like a small spacecraft built for one body. And the thermal part is much more important than most people realize. A human body at rest produces roughly around 100 watts of heat, and during hard work, that number can rise several times higher. An astronaut doing physical work outside a spacecraft can generate several hundred watts of waste heat. That heat has to go somewhere. On Earth, your body dumps heat into the air with sweating, breathing, and blood flow near the skin. In space, those methods don't work normally because the surrounding environment is vacuum. So the suit has to remove that heat for you. That is why modern EVA suit systems use liquid cooling garments, tubes carrying water near the skin, insulation layers, reflective outer materials, and systems that reject heat to the outside. The suit also must protect the astronaut from the opposite problem, losing too much heat in darkness or low radiation conditions. So once again, the thermal challenge goes in both directions. The system must stop overheating and overcooling at the same time. That is the detail most people miss. A A spacesuit is not mainly fighting cold space. It's fighting thermal instability. It's trying to keep a human body inside a narrow, safe range while the outside environment offers almost no stable middle ground. And that leads to the main point. Human biology evolved in a very narrow set of conditions. We evolved with atmospheric pressure, breathable air, weather, oceans, shade, thermal buffering, and a planet that constantly smooths the extremes. Your body expects all of that. It's tuned for one world. Take that away, and even basic ideas like hot and cold stop working the way your instincts expect. In space, the problem is not just that it's cold. The problem is that the whole system your body depends on is gone. Pressure is gone. Air is gone. Thermal moderation is gone. The rules become hostile immediately. That is the terrifying truth. The universe doesn't care what temperature feels like to you. It doesn't care that your body thinks in terms of warm, cold, wind, sweat, and shade. Outside Earth's narrow protective band, those familiar ideas start to break apart, and your body can't adapt fast enough to matter. And that pushes the tension higher again, because once human survival drops away, the next question becomes even extremer. What does cold even mean in the parts of space where almost nothing exists at all, where matter becomes so sparse that even the idea of temperature starts getting hard to use? Interstellar and intergalactic space are so empty that even the word cold starts becoming misleading. Up to this point, cold has already broken a lot of normal intuition, but this is where it really stops behaving like anything from daily life. When people picture outer space, they usually think of emptiness in a vague way. They know there's not much there, but the real scale of that emptiness is much harder to process. And once you understand it, you also understand why temperature in deep space is such a strange topic. Inside the Milky Way, the average density of the interstellar medium can be around 1 atom per cubic centimeter, though that varies a lot depending on where you are. Some regions are denser, some are much thinner. But even that average number is already extreme when you compare it to Earth. Air at sea level contains on the order of 10 quintillion molecules per cubic centimeter. So the difference is not just that interstellar space is thinner, it is thinner by an amount so huge that normal experience stops helping. Interstellar space is not like standing in very thin, cold air. It is a completely different regime of existence. There is so little matter there that the normal ways heat moves and the normal way your body thinks about temperature stop being useful. And then it gets even more extreme between galaxies. Intergalactic space is emptier still. In the most rarefied regions, densities can fall to a tiny fraction of a particle per cubic meter. That is so far beyond ordinary vacuum that it barely connects to anything human beings deal with directly. Even many of our best laboratory vacuums are not routine approximations of those conditions on a large scale. The darkness between galaxies is not perfectly empty, but it is so sparse that it pushes matter into a regime where intuition almost completely fails. That is why talking about the temperature of space becomes dangerous, unless you also ask what exactly you mean. Temperature sounds like one clear property, but in these environments, you have to be careful. A gas can have a very high temperature if its particles are moving very fast, even if there are almost no particles present. That means some regions of space can contain plasma at millions of degrees and still not feel hot in any normal sense. That sounds like a contradiction, but it is not. Temperature describes the average energy of particles. It does not automatically tell you how much total heat is available to transfer into something else. If there are very few particles, then even if each one is moving with high energy, there may still be very little actual heat exchange. So you can have extremely hot plasma in terms of particle energy, but because the density is so low, it does not behave like being inside a furnace on Earth. This is one of the hardest things for people to absorb, because daily life trains you to think of hot and cold as something immediate and obvious. A hot oven feels hot because dense matter and radiation are delivering energy to you efficiently. In deep space, the relationship between temperature and experience gets broken apart. You have to ask, temperature of what? How many particles are there? How fast are they moving? And how effectively can they transfer energy? That is the real theme of this whole section. Once matter becomes sparse enough, temperature is still meaningful, but it stops being intuitive. Now go one step further. If an object is isolated far from stars, far from planets, far from active galaxies, what happens to it over time? It cools. An isolated object in deep space will keep radiating away its own heat. If nothing nearby is warming it significantly, it will gradually move toward equilibrium with the surrounding radiation field. In today's universe, that means drifting towards something like the cosmic microwave background, around 2.7 Kelvin, unless some local heat source changes the situation. Not instantly, and not in some dramatic movie way, but steadily, over time, the object loses energy. That is the default trend. In enough isolation, cold wins. That point matters because it shows that cold is not only a condition in special places, it is the long-term outcome of enough emptiness and enough time. If you remove the heat sources and leave matter alone in the deep universe, it tends toward the background. And that is where the scale of the problem becomes hard to mentally hold. You are not talking about a cold room, a cold day, or even a polar night. You are talking about regions so empty that matter is barely there, and for that almost nothing to still have a temperature that matters scientifically. So when you say interstellar and intergalactic space are cold, that is true. But it's still not the full truth. The deeper truth is that they are cold in a regime where the normal meaning of hot and cold starts breaking apart. Matter is too sparse. Heat transfer is too weak. Radiation dominates. Background temperature becomes important. Local particle energy can be high even when total interaction is tiny. That is why this part of the story feels so unsettling. The deeper you go into empty space, the less human language about temperature seems built for what is actually there. And that raises attention again, because once you accept that deep cold and near empty space can still hide strange activity, the next question becomes even more surprising. Can a world be covered in ice, sit in brutal cold, and still stay active underneath? A world can be frozen solid on the outside and still stay active underneath, and that's where cold space starts getting even stranger. By this point, the easy version of the story is already gone. Cold is not just a threat, and it's not just a background number. It shapes planets, telescopes, spacecraft, nebulae, and even the deepest physics around black holes. But ice worlds add another twist, because they show that extreme cold doesn't automatically mean a dead world. Europa is one of the best examples. Its surface is brutally cold, around 100 Kelvin on average. That's about minus 173 degrees Celsius, or about minus 280 degrees Fahrenheit. Enceladus is also deeply frozen at the surface. If you only looked at those surface conditions, you might assume both worlds are basically inert blocks of ice, but that's not what the evidence shows. Europa has strong evidence pointing to a subsurface ocean beneath its icy shell. Enceladus goes even further. Cassini directly sampled water-rich jets erupting from Enceladus near its south polar region. That means this moon is not just hiding liquid water inside. It is actively throwing material from that internal environment out into space. So the next question becomes obvious. Where does the energy come from? The answer is that external cold is not the only thing that matters. Internal heat sources can fight back. One of the biggest is tidal heating. When a moon orbits a giant planet, the planet's gravity can flex and squeeze the moon over and over again. That constant deformation creates friction inside the moon, and friction generates heat. Over time, that can keep parts of the interior much warmer than the surface. Radioactive decay can also add heat from within, so even under some of the coldest surface conditions in the solar system, liquid water can still persist below the ice. That is one of the biggest paradoxes in planetary science. A moon can look completely frozen from the outside and still hide a warm, dynamic interior. And once liquid water enters the picture, the stakes rise immediately, because now you're not just talking about geology, you're talking about chemistry, and maybe in the long term, habitability. That is why Europa and Enceladus matter so much. They show that cold does not always shut a world down. Sometimes cold traps the interesting stuff under the surface instead. And then Titan pushes the idea in another direction. Titan is cold enough to make Earth-like weather happen with completely different liquids. Its surface temperature is around 94 Kelvin. That is about minus 179 degrees Celsius or about minus 290 degrees Fahrenheit. At those temperatures, water is basically rock like ice, but methane and ethane can exist in liquid form near the surface. That means Titan has lakes, rivers, rain, clouds, and a weather cycle, but built out of hydrocarbons instead of water. That is not speculation. That is based on data from the Cassini-Huygens mission. Titan is one of the clearest examples of how extreme cold does not erase planetary processes. It changes the materials involved. On Earth, water runs the weather. On Titan, methane and ethane step into that role. So again, frozen does not mean inactive. It means the whole system is playing by different thermal rules. And Pluto and Triton keep reinforcing that lesson. Both worlds are extremely cold, but both show signs that matter still moves, changes, and reshapes the surface over time. Nitrogen ice, methane ice, seasonal transport of volatile materials, thin atmospheres, and active resurfacing all show that low temperatures do not make a world irrelevant. They make it alien. That is the real point here. Extreme cold changes the materials in play, but it does not cancel physics. It changes what melts, what flows, what condenses, what evaporates, and what counts as weather or geology. A world that looks frozen and lifeless by Earth standards may still be active in a completely different way. And this pushes the main theme of the script even higher. The terrifying truth is no longer just that space is cold enough to kill you. It is that this cold creates entire classes of worlds that operate by rules that barely resemble Earth. Frozen crusts can hide oceans. Cryovolcanoes can erupt. Hydrocarbon rain can fall. Ices made of nitrogen or methane can move across landscapes the way water or rock does here. So cold is not only a survival problem, it is a world-building force. It creates environments stranger than most people ever imagine when they hear the word frozen. And once you see that, the next step gets bigger again, because now the question is no longer just how cold space is today. The question becomes where all of this is going. Because if the universe has been cooling the whole time, what does the far future look like when that process keeps going and going and going? The cold of space is not just about where the universe is now, it's also about where the universe is going. That is the biggest scale shift in this entire story. Up to now, we've talked about cold as a condition around astronauts, spacecraft, planets, nebulae, and deep space. But the deeper truth is that the universe itself has been cooling for its entire history, and that process is still happening. So when you ask how cold space really is, you are not just asking about a place. You are asking about a long trend stretching across cosmic time. The reason is simple in principle. As the universe expands, radiation gets stretched, its wavelength gets longer, and that means its energy drops. So the background radiation of the universe keeps cooling as space keeps expanding. The cosmic microwave background is about 2.725 Kelvin today, but it was hotter in the past, and if you move far enough into the future, it will be colder than it is now. That means the universe is not sitting at some fixed thermal state. It is still sliding downward. And that matters because accessible energy is what allows things to happen. Big temperature differences, concentrated fuel, collapsing gas, active stars, and strong gradients all make the universe dynamic. As those differences flatten over time, the universe does not necessarily disappear, but it becomes less active. Less useful energy is available for doing work. Less structure is being built. The long-term trend is not toward more motion and complexity. It is toward less. And that brings up the next hard fact. Stars do not burn forever. Right now, stars are still being born, but star formation is already much lower than it was billions of years ago. In the earlier universe, galaxies had more available gas and built stars at a much higher rate. Over time, that supply gets used up, locked into stars, blown away, or left in forms that are harder to turn into new stars. So the great age of star birth does not continue forever. Eventually, long-lived red dwarfs dominate because they burn fuel very slowly and can last for enormous spans of time. Larger, brighter stars live faster and die earlier, so the future universe becomes dimmer not all at once, but by stages. The bright, busy era fades. The cosmos becomes less luminous, less crowded with new stellar activity, and more dominated by old remnants. That is the beginning of the path people call heat death, but that phrase can be misleading if you picture some sudden event. It's not a giant freeze wave sweeping across the universe. It's not one moment when everything ends. It's a very long decline. White dwarfs cool, neutron stars cool, brown dwarfs fade. Stellar remnants that are hot today lose energy over vast stretches of time and become colder and dimmer. Even though some of those timescales are far beyond the current age of the universe, the direction is clear. The future is colder than the present, and the present is colder than the past. So the universe is aging thermally. That's important because it changes the emotional shape of the story. The future of the universe is not mainly about one dramatic catastrophe. It's about exhaustion. It's about gradients flattening out. It's about energy becoming harder and harder to use. Structures may still exist. Matter may still be there. Black holes may still remain for an incredibly long time, but the overall system becomes less capable of dramatic activity. That is what heat death really points to. Not everything freezing in one instant, but the slow loss of usable differences. Work becomes harder to extract. Light becomes rarer. Active processes become less common. The universe does not end with a bang in this picture. It thins out thermally. And that's more disturbing in a way, because it's not violent enough to feel like a normal ending. It's a slow surrender of energy contrasts, a long movement toward colder, dimmer, quieter conditions. So when someone asks how cold space really is, the deepest answer is not just a number, like 2.7 Kelvin, and it's not just a description of vacuum or shadow or distant planets. The deepest answer is temporal. Space is cold because the universe has been cooling for 13.8 billion years, and that cooling is still underway. The cold we see now is part of a much larger arc. That is the biggest stake of all. Cold is not only a danger around us, it is the direction of cosmic history. And that means the final step in this script has to pull everything together, because once you see cold as a force that breaks intuition, shapes stars, controls planets, defines telescopes, challenges biology, and points toward the future of everything, the last question becomes unavoidable. What is the full truth hiding behind the simple phrase, "Space is cold"? You started with a simple idea. Space is very cold, and by now that idea should be completely broken, because temperature alone was never enough to explain what is really happening out there. To understand cold in space, you had to add other pieces your instincts don't naturally track. You had to think about density, because a thin gas and a dense gas don't affect you the same way even if the temperature numbers sound similar. You had to think about radiation, because in vacuum, heat often moves by light instead of air or water. You had to think about pressure, because pressure changes whether liquids boil, freeze, or stay stable. You had to think about emissivity, reflectivity, illumination, and timescale, because in space, a surface can get hotter or colder not just based on where it is, but how it's exposed and what it's made of. So the first thing cold space destroys is your intuition. That matters because the original question sounded easy. How cold is space? It sounded like it should have one number as an answer, but it never did. The deeper you went, the more that one number picture fell apart. Space is not just cold in the way a freezer is cold. It is cold inside a vacuum, cold inside a radiation-dominated environment, cold inside a universe with a background temperature but also local extremes, rare exceptions, and strange thermodynamic rules. By the time you really understand it, the concept itself has to be rebuilt. And once that happens, the next truth becomes much harder to ignore. Cold space does not just defeat your intuition, it defeats you. Human beings survive inside a very narrow thermal envelope. We are protected by atmospheric pressure, by breathable air, by wind and water and clouds and oceans, by a planet that stores heat and redistributes it, by an environment that smooths out the worst extremes. Your body expects all of that every second it is alive. Strip that away and you do not just enter a cold place. You enter a place where the rules your biology depends on no longer work. That is why space is so dangerous. The threat is not one clean temperature number. The threat is the collapse of all the familiar thermal systems that make life possible. Pressure disappears. Normal heat transfer disappears. Sunlight and shadow become extreme. Your body becomes a biological system operating in conditions it was never built for. So the danger is not just low temperature. The danger is that the middle ground vanishes. But this is where the story turns into something even bigger, because cold is not only destructive, it is also constructive. Cold molecular clouds collapse into stars because lower temperatures make it easier for gravity to win. Cold interstellar environments preserve molecules and support chemistry that hotter regions would erase. Frozen worlds like Europa, Enceladus, Titan, Pluto, and Triton prove that cryogenic conditions do not end activity. They redirect it into forms that look alien to us. Infrared telescopes like James Webb have to become extremely cold just to see the oldest, faintest light in the universe. So cold is not just a side detail in astronomy. It is built into the machinery of the cosmos. That is one of the biggest conclusions of the whole script. The same cold that would kill an unprotected person is also part of the reason stars form, molecules survive, planets evolve, and cosmic history can be observed. Cold is not just one more property of space, it helps organize the universe. And then the final scale shift arrives, because cold also points toward the fate of everything. The cosmic microwave background tells you the universe was once hotter. Cosmic expansion tells you it's been cooling for billions of years. Black hole thermodynamics tells you even the strangest objects in the cosmos are tied to temperature and entropy. The future of the universe points toward further cooling, further fading, further loss of usable energy over unimaginable spans of time. So cold is not only a fact about space today, it is part of the timeline of reality itself. The universe did not begin cold, but it is cooling into its future. Every galaxy exists inside that trend. Every star shines temporarily inside that trend. Every planet, every cloud, every black hole, every living thing is inside a cosmos moving along that thermal direction. So here's the full reveal. The terrifying truth about how cold space really is much bigger than a survival fact. It's bigger than saying space is near absolute zero. It's bigger than saying shadow is deadly and sunlight is harsh. Space is cold enough to break the way your mind first tries to understand temperature. Cold enough to make vacuum more dangerous than the word cold can capture. Cold enough to control how stars are born and how molecules survive. Cold enough to force our most advanced telescopes into cryogenic silence so they can detect the ancient light of the early universe. Cold enough to show that even black holes belong to thermodynamics. And cold enough to hint at the long future of a universe still cooling with time. That is the real answer. The darkness above you is not empty in the simple sense, and it's not just cold in the simple sense either. It's a vast thermodynamic system shaped by vacuum, radiation, pressure, energy flow, and time, sitting only a few degrees above absolute zero on average, but capable of pushing matter into extremes far beyond anything human instincts were designed to understand. And once you see that clearly, the phrase "space is cold" stops sounding like a fact. It starts sounding like an understatement. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.